going to give this, this message. Ok, obrigado a todos pela presença. Essa apresentação vai ser feita em inglês, então eu gravei exatamente o mesmo conteúdo em português e vai estar no link aqui embaixo, né? Está aparecendo aí? Então vocês podem seguir por esse link. E agora eu vou começar. Dr. Hochbein, you have something to say? Dr. Hochbein, you can hang up from Google Meet because it's going to be some return, okay? Okay, thank you, Mariano. I have muted Dr. Hochbein. Just some technical issues before we can start. But okay, now I can start with the presentation by thanking everyone in the committee for agreeing to be here today. I'm going to present my PhD research, which is entitled Residual Stress Prediction through Numeric Simulation and Influence over the Fatigue Life of Crankshafts Subjected to Deep Rolling, which is a mouthful, actually. So we can break this down into an important surface integrity parameter, such as residual stress, also an important prediction tool, numeric simulation, a design requirement, in this case fatigue, and also processing, which was studied deep rolling. The fact that we are working with crankshafts, I think it's circumstantial in this occasion because the same methodology, the results, and the way to analyze the results can be overflown and be applied to other components, processes, and even industrial sectors. So if we can start the presentation here by the contents. I will give a brief introduction with some motivation and a literature review, followed by the outline of the objective and the approach taken to reach such an objective, followed by the numerical and experimental procedures that were used to obtain the results, and finally some conclusions and outlook for future work. So very basic, it's no surprise to anyone that most engine developments nowadays are driven by fuel consumption and emissions regulations. So the current trends will be, aside from electrification, engine downsizing, turbocharging, alternative fueling, and all of that will cause an increase in efficiency, a decrease in weight, and an increase in net power. So all of that combined will cause also an increase in the mechanical loading over the engine components, such as the crankshafts. So to overcome this challenge, we obviously need to correctly select and design select the material and design the crankshaft. But also we need to understand how the loading loads the operational loads are being applied to this component, and how the manufacturing processes can help to increase the fatigue life of this component. With special attention to the stress concentrators, which in this case will be the fillet radius and more precisely the bottom fillet radius. And I have a quote here from Dr. Hochbein, whom I have the pleasure here of his presence today in the committee, that stated that only 50 grams of a 25 kilogram crankshaft are responsible for its endurance strength. So he's talking about the fillet radii. So let's focus on that. But why we are studying deep rolling? It holds 75% of the current passenger car engine crankshafts market. And that's no wonder, because when compared to other processes, it has the potential to generate the highest residual stresses and deliver the best fatigue limits. but not only in the automotive sector, but also turbine blades, railway axles, and high-pressure cylinders are also components and industries that apply similar processes, and they all have critical components with high fatigue requirements, and are always seeking for both product and process optimization. So again, everything that I'll say here can be overflown into these other industrial sectors. Okay, so let's put everyone in the same page in terms of the crankshaft manufacturing chain, with a special look on residual stress interaction between the processes. So first, for a casted crankshaft, we would have casting first, which would theoretically not introduce significant residual stresses to the component. And after that, we have machining and surface treatment. And in this case, we do have two processes that can interact between each other in terms of residual stress generation, especially at the fillet radii region. That would be deep rolling and milling. And finally, we have inspection with balancing. So by the end, for a cast iron crankshaft, we would have a graphite nodule surrounded by ferrite inside a perlitic matrix. So let's take these two main processes and study a little bit more about them. I have a quick video here that I'm going to show you, and hopefully will play for everyone. So crankshaft machining is done with all bearings at the same time. And we do have some studies on it in the literature, but only a few on residual stress generation. And if we think how residual stress are generated through crankshaft machining, it is similar to downcut milling, which starts with the maximum chip thickness, which transduces more heat into the workpiece and favors tensile residual stresses. So we are expecting tensile residual stresses to be generated by this process. Moving on to the deep rolling process, and I have another video here that I stole from the people from Hagenscheidt. And we also treat all fillets simultaneously. We do have some relatively extensive literature on this process, but it is mostly experimental, and only a few studies try to actually model it with a numerical tool. So that opens a gap for us to address. And this process, just to explain a little bit better, the force is applied through the roller head down to the angled rollers, specifically at the regions of the fillet radii. We're creating this ovalized residual stress field, which will be applied not constantly, this force, but alternatively. So in the bottom part of the crankshaft, as you can see here in this graph, it is loaded with twice the force than in the top, and that is because we do have tensile stresses appearing at the bottom part when the engine is under operation. So this process aims at generating compressive residual stresses in that region to overcome these tensile stresses, operational tensile stresses. So on the relationship between residual stress and fatigue, we already know that the crack preferential site for crankshafts appear at the fillet radii and propagate through the web. So that is well known. And when you think about the relationship between acting stresses and residual stresses, we can use the superposition principle. So what we need to do is to analyze a combined stress state to understand how fatigue would happen in this case. And I do have here two experimental works here. The first one done by Mitsubayashi, where he tried to, where he studied the crack propagation rate relationship with the peak residual stress region for shot pinion gears. And what he could observe in his fatigue tests was that the crack had slowed down during precisely the region where residual stresses were at their maximum. So that was interesting to see. And also interesting is another study by Michaud, where they studied actually crankshafts and could see that the crack propagation rate also slowed down for a given bending moment during fatigue tests, and the crack was actually arrested for a lower bending moment that was applied. So it was also interesting. And finally, for the deep rolling simulation advancements, I have also separated two main studies here. The first one done by Savic, where I guess this is the only study that I could find that could capture all aspects of the deep rolling modeling and simulation for crankshafts. But unfortunately, the authors could not validate their residual stress results with measurements taken under the exact same conditions. So that was unfortunate. But I have another study here on deep rolling, but not specifically on crankshafts, as Hassani Gangaraj has studied the deep rolling made on railway axles through a numerical experiment that actually have inspired some part of this thesis. The authors have changed some of the key deep rolling parameters and got a holistic understanding on how these process parameters changed the residual stress generation for this specific component. So I guess this opens an opportunity for us to correlate the residual stress parameters, the deep rolling parameters with residual stress and fatigue performance for crankshafts. Okay, so with this brief literature review, I guess we can outline the objective, starting with the observation that there is currently no integrated residual stress prediction tool together with fatigue performance. And we can also take advantage of the residual stress equilibrium and superposition principles to state the hypothesis that the residual stress distribution due to the process parameter variation plus the operational loading to which the crankshaft is subjected can lead to an alteration in its fatigue behavior. So the actual objective of this research is the understanding and the prediction of the influence of deep rolling process parameters over the fatigue performance of crankshafts. So in order to reach such an objective, we have separated this research into, we have outlined 3 research questions. The first one being how to model the process to predict residual stress generation. The second one being what changes are brought to the residual stress state by varying some of the key deep rolling parameters. And finally, the third research question asks, can the final stress state after deep rolling plus bending moment simulation and experimentation be linked to the fatigue crack site? So in order to respond to these 3 questions, we have used an approach here for the first one, where we obviously simulated, created a model for the process, did some residual stress measurements in order to validate that model. That was extensively used for the second research question, where we have done a numerical experiment varying some of the deep rolling key process parameters. And finally, for the third research question, we have congregated fatigue tests with the results from the simulation of deep rolling plus bending moments into a single way to analyze those results and get some correlation. So let's move on to the numerical procedures first. And I guess I should say that this research topic started in 2013 together with the industry and with my master's, which was finished by 2015, where we could develop the deep rolling model and have it partially validated. So in this thesis, we will bring some changes and advancements into this model in order to do a complete validation and also perform the numerical experiment. So before we enter into the actual deep rolling modeling. We need to characterize the material that we are working with to select the best commercially available material model. So first, what we did was to do monotonic loading tests with standardized specimens that were inputted into a single element model, and the name already says it. It's a single hexahedron element with a prescribed displacement exactly the same as the one that we have done with strain-controlled reverse loading tests. So we compare these two, the results from experiments with simulation by changing some of the material models that are commercially available at Abacus, such as cast iron plasticity, isotropic, kinematic, and also a combined isotropic kinematic model. Okay, so on the boundary conditions of the deep rolling model, it's pretty straightforward. We have a fixed roller so the crank pin rotates around this fixed roller while the roller applies a realistic load cycle taken from the machine. So here you can see the ups and downs from of the rolling force being applied, and that accounts for the highest load being applied at the bottom part of the crankshaft and the minimum load being applied at the top part, again, because of fatigue requirements. So after this deep rolling step, we have added a bending moment step to account for the operational loads that the component will be subjected. And for the numerical experiment, we have chosen three main process parameters here to change. The first one being the rolling force. So from a baseline of 100% of rolling force, we have ranged from 33 to 133%. For the roller angle variation, we have changed between 30 and 45 degrees, and also studied rolling cycle variation with so-called old and new cycles. But what we will see is that the rolling force variation was the most important parameter in residual stress generation. So we will take this process parameter and vary it also experimentally. But before we enter into the experimental procedures, we need to just clear out how to assess the crack perforation, the crack initiation preferential site through the simulation. So we will take an extract from the fillet radii on both top and bottom regions, and analyze this region here between node rolls 6 to 11. So it will be the most impacted region by the rolling during the process. And what we did was to set a cylindrical coordinate system at this point, where the radial direction points towards the center of the fillet, the hoop direction, or theta, points towards, it's along the circumference of the fillet, and Z, or axial, is perpendicular to the first two ones. So again, if we think about a crankshaft that is supported by the bearings, and combustion forces occur during at the top, that center, we will experience a bending moment acting to compress the top part, but to bring tensile stresses into the bottom part. And if we think that fatigue would mainly occur when we have tensile stresses during cyclic loading and local plastic deformation, this bottom part here is where is the critical region for us to assess. So we are expecting a mode 1 type of crack here to appear in the bottom part in the hoop stress direction. So let's focus on that. On the experimental procedure, starting with the residual stress measurements, we have counted with the expert assistance from our colleagues at Stress Tech in Germany to help us to develop a procedure to assess this very intricate and complex geometry, such as the crankshaft fillet radii, region. So they have measured stresses for us in axial and hoop direction along depth. So they had to polish the surface as well. So what we did, we took this developed procedure and replicated and expanded it together with our friends from the Lightweight Structures Laboratory of IPT, using the exact same machine as stress test used in Germany, also with all specimen batches produced with different rolling force, ranging from 33 to 133% of rolling force. So we have created basically 3 stations here. The first one being the residual stress measurement station. The second one, we measured the depth that was electropolished by the third and final station. Still on residual stress measurements, we had to come up with a template here to reposition this specimen every time that we had to electropolish it and put it back into the machine. So a repeatability and reproducibility analysis will show that this was key for us to have reliable results by the end of our investigation. And I don't know if you could see that, but we had to section or cut the crankshaft so we could measure residual stresses using the XRD technique. So it would be impossible to measure a crank throw as it is. And we want to know how much of the sectioning will impact in terms of residual stress relief. So we applied a first cut that was deemed not to impact too much into these 2 measured regions at the top and bottom parts. And then we have applied a second cut to produce the final geometry that was measured throughout the entire measuring campaign. So the difference between the results from before and after the second cut will give us an idea on how much stress relief we are dealing with. And finally, for the experimental procedures, we have the fatigue tests done with actual crankshafts with a resonance fatigue test rig designed by my colleague Cantizano, where he uses an electrodynamic shaker to input forces into a 2 degree of freedom system composed by a crank pin between 2 inertia arms in order to input high bending moments. And again, we have done these fatigue tests with all specimen batches produced between 33 and 133% of rolling force using the staircase method. So after each test, we have used dye penetrant inspection to see if there were any superficial cracks. And after we open the specimens up using a hydraulic press, we could have a good look at the fracture surface. All right, so reaching out to the results finally, and starting with the addressing of the first research question. Again, just to remind it how to model deep rolling process to predict residual stress generation. First, we need to correctly select a material model to be inputted into our deep rolling model. So the first thing that we did was to get the monotonic results and inputted them into the single element model. And the results will be compared to the reverse loading test that we have made. So the first material model that we have assessed is the cast iron plasticity. And you can see that this model is not suitable for this application, since it is basically an isotropic model that allows the user to input different tensile and compression stress strain curves. Similarly, the isotropic model is also not suitable for us. When we moved on to the kinematic model, things got a little bit better, but only after we have used a combined model with isotropic and kinematic hardening, then we got a result that was more likely to be used. So this combined model will be applied into the deep rolling model for the rest of the research. So on the deep rolling model, we can first assess it in terms of in a qualitative way. So we can see that the overall aspect of the results are generally according to expectations. We can see that the top was less strained and stressed when compared to the bottom. So the bottom would be the place where we have the higher forces being applied. So we will take here and extract from both top and bottom regions to understand how stresses are being generated. So starting with the top region, we can see that for both hoop and axial directions, residual stress directions, we have compressive stresses at the surface, moving on into an internal peak and transitioning into the tensile stresses. So to account for the equilibrium principle. So this region here between node rolls 6 and 11 will create this in-depth area here that we will compare with the residual stress measurements that we did. And we can generally state here that both shape and magnitude were in agreement for both directions. And obviously, we can see some differences, and they can arise from different sources of disparities. So the first difference that we noticed was right at the subsurface here, between 50 and 100 microns, where we have a steep gradient of the stresses, so they rise and then are quickly recovered afterwards. So this feature here of the residual stress measurements were explained by the machining influence that a hypothesis on the machining influence. So we have measured a specimen that didn't pass through deep rolling, was only machined. And what we can see for the top part is that the stresses start at a tensile, at a relatively high tensile stress, but are quickly recovered and become compressive to account for the equilibrium principle. And also, further in depth, we don't see much of a residual stress imprint, so we are attributing that to casting. But if we look at how the bottom part behaves, we think that this disturbance might be introduced by the machining process, which could have impacted in the final residual stress state after deep rolling. Another source of disparity is obviously the sectioning influence. So if we take measurements before and after cutting, we can see that for the top region, we don't see much of a difference, much of a stress relief. But for the bottom part, that is a important stress relief. Most likely because the cut was made very close to this region. So any differences in terms of magnitude between simulated and measured stresses can be attributed to this influence. And finally, a reproducibility and repeatability analysis show that the template indexers are very much needed for this endeavor, as we have we are dealing with a very complex and intricate geometry at the crank pin fillet radii. So we do need to be able to reposition the sample every time we needed to electropolish it. All right, so moving on. So with the deep rolling model validated, we can move on to the second research question, where we ask how the key process parameters are changing the residual stress state. So starting with the numerical experiment that will use extensively the deep rolling model, we can see that first for the rolling force variation, we see that it is, if we input higher forces, we will see higher residual stress peaks further in depth. That is very clear for us. If we are looking for the best fatigue performance, then the 133% model would theoretically derive the best results for us. But what we can see is that the material is saturating to this process. As if we keep increasing the rolling force, we don't see much of a gain in terms of residual stress, so as you can see here. When we look at the others process parameters that were varied, for roller angle, we can see that for 35 and 40 degree of roller angle, we got the best residual stress peaks inside, but with a very narrow operational window when we compare to the rolling force assessment. And the same thing can be said by the rolling cycle, where the new cycle was constantly, but only marginally, more compressive than the old cycle, with a very narrow operational window. Again, so we have selected the rolling force parameter to be varied experimentally, and just a reservation needs to be done at this point, as the 100% of rolling force specimen batch was produced at a different facility than the other batches. So just keep that in mind. So first, for the 100% assessment, we can see that the bottom and top stresses are very close to each other in terms of magnitude, and that is not something that we would expect, since the bottom part has been deep rolled with twice the force as the top part. But if we recall the sectioning influence study that we made and add those deltas into the curves, we can then see something that was more likely to have happened with the bottom part being more compressive than the top. So that makes sense. And for the assessment of the others, the other specimen batches that were rolled by the company Hagenscheidt in Germany, we can also see, again, for the subsurface here, between 50 and 100 microns, that the stresses also have a steep gradient and then are quickly recovered into a in-depth peak. So that, again, brings strength into the hypothesis that the machining is indeed influencing in the final residual stress state after deep rolling. And again, with the reservation that not all specimen batches were rolled in the same facilities, we can approximate all curves using third-degree polynomials quite well. So the same conclusions here were already shown by the numerical experiment results for rolling force variation. So we can see that higher, an increase in rolling force will produce higher residual stress peaks, further in depth, and also the transition for the tensile part would be also further in depth. And by the same analysis made before, we can also see that the material is saturating to the deep rolling action here. As we increase the rolling force, we see, I'm sorry, we see that we don't have much of a gain in terms of residual stress peaks. So if we keep increasing it, it would deliver possibly marginally higher residual stresses and better results in terms of fatigue. And that's what we are treating here in the third research question, where we ask how can the final residual stress state after deep rolling and bending moment simulation and experimentation be linked to the fatigue crack site. So for that, we have taken the results from the staircase methodology that were all statistically valid. and normalizing the results around the 100% test batch, so the fatigue limit here would be equal to 1. We can see that, for instance, for the 33% test batch, we got 0.75% of fatigue strength. For the 67%, very close result to the 100% one, 0.96. And the 133% test batch was delivered the best fatigue results with 1.15. If we take a non-failed specimen and analyze it under with dye-penetrant inspection, we can see a very small crack at the surface here, at the fillet region. And once we break it open in the hydraulic press, we can see a shallow crack, and this shallow crack was attributed to the crack arrest phenomenon. So, the depth of this crack would also depend on, in terms of the deep rolling process parameter that we are dealing with. So for this picture that I'm showing is for the 100% rolling force test batch. And I guess this table here summarizes everything, so I'm going to break this down. First, we can see that the fatigue limit and the residual stress peak magnitude are closely related, as we got here. When we doubled the force between 33% to 67%, we got approximately 20% of a fatigue increase. And when we doubled again between 67% and 133%, we got also, again, 20%. So as we keep doubling it, the results are showing that the material is saturating. And the same thing was shown by the residual stress peak magnitude assessment. And again, when we have analyzed the arrested crack depth, we can see a close relationship with the residual stress peak depth for all of the specimens analyzed. So I guess this only brings some clarity to the matter. If we take that same picture of the shallow crack and amplified it, so we can see here the fillet radius and the crack here on medium gray in the middle, and superpose the residual stress graph, we can see that the residual stress peak acts as a barrier for the to hold the crack from keep propagating. And if there is enough energy to overcome such a residual stress peak, then we will have failure, as there is nothing to hold this crack from propagating other than the bulk material in this case. So for this last final two slides that I have, I guess they show the clearest evidence that the deep rolling model is capable of capturing all aspects of the process, as we did a methodology here where we took an open fractured crankshaft and put it under this microscope sideways, so we can get a picture here of a profile picture where we can see the bearing surface, the fillet radius, and the crack location. So we have the crack outline with this view. And if we take the results from the deep rolling process, the deep rolling plus bending moment simulation, and analyze the exact same region, and superpose these two images, we can see that the highest stress site matches very well the crack location. And this was done for the 100% test batch, and we can expand it to the others. Sorry. We can expand this analysis to the other test batches. So for instance, for the 33% test batch, we saw that the crack was somewhat in the middle of the fillet, and the model predicted the highest stresses to be between node rows 9 and 10. And if we analyze the 133% test patch, we can see that the crack has moved towards the web or the counter rate. And also the prediction tells us that the highest stresses would be between node rows 12 and 13. So this shows how this model is robust, as we are changing the input parameters, and we are obtaining some very close results and I would say reliable results. Okay, so for the conclusions, I guess we can bring back the first research question where we have simulated the deep rolling process and made a validation of such simulation with residual stress measurements, which show that we have good agreement between curves in both stress directions, in both magnitude and shape. So the model was considered validated at this stage, and it was extensively used for the second research question, where we have varied the experimental with a numerical experiment using different deep rolling parameters, and selected one, in this case, rolling force for a experimental variation, where we could, by the end, do a complete deep rolling parameterization to get a good feeling, a holistic feeling on how the parameters are changing this process. And finally, for the third research question, we have congregated fatigue results with deep rolling plus bending moment simulation, so both processing and operational loads being put together here for the introduction of a residual stress assessment into the fatigue evaluation of this specific component. And I guess I guess this methodology, everything that was done here, from the deep rolling modeling to the residual stress assessment and how to assess the final fatigue and simulation results, can be applied here for other aspects, other challenges, such as changing other parameters of the same simulation and make combinations between parameters, as well as we have the test rig prepared for torsional loading as well, so we can apply the exact same prediction tool here for torsion. Also, we are working with some different ways to obtain the fatigue limit through infrared thermography, and obviously everything that was stated here can be used for other components, processes, and industrial sectors. I'm sure of that. And finally, I'll just take a moment here to acknowledge the crucial help that we had from our colleagues of Hagenscheidt in Germany, as well represented here by Dr. Hockmein, and as well as people from StressTech and my good friends from IPT. This project also received funding from CAPI, CNPq, and Embrapi. And without such funding, I wouldn't be able to do any of the tests that I did, or even be able to go to Canada for a year. And also, I'd like to thank my colleagues and friends from CCM here in Brazil, and also my friends from the Fatigue and Stress Analysis Lab, represented by Professor Jahed, and also my friends from the Composites Research Group, represented by Professor John Montezano. E obrigado aos meus amigos e familiares. Muito obrigado, thank you, and I guess that's it. Thank you.